Ever wondered how high-performance thin-layer chromatography works? Today, we dive into this fascinating topic. High-performance thin-layer chromatography, or HPTLC for short, is a sophisticated analytical technique that is vital in the field of chemistry. It's a technique that allows us to separate and identify the different components within a mixture, with a precision and efficiency that's truly remarkable. In this video, we will explore the theory behind HPTLC, the instruments and plates involved, and the various development techniques used. We will also touch on how HPTLC scanning and evaluation takes place, and look at some of the many applications of this technique. From automated multiple development to horizontal TLC and other development modes, we'll be lifting the lid on these complex processes, making them easy to understand. So if you're ready for a deep dive into the world of HPTLC, you're in the right place. Stay tuned as we delve deeper into the science behind HPTLC. First off, let's explore the theory that makes HPTLC possible. High-performance thin-layer chromatography, or HPTLC, is a sophisticated version of TLC, a technique that allows the separation of mixtures based on differential adsorption. In the world of HPTLC, we're dealing with two main players, the stationary phase and the mobile phase. The stationary phase is a thin layer of adsorbent, often silica gel or alumina, coated onto a glass or plastic plate. The mobile phase, on the other hand, is a solvent or mixture of solvents that travels up the stationary phase. Here's where the magic happens. When a small amount of the mixture to be separated is applied onto the stationary phase, and the mobile phase is allowed to ascend, the components of the mixture start to move. But they don't all move at the same pace. Some components have a greater affinity for the stationary phase and move slower, while others have a greater affinity for the mobile phase and move faster. This differential movement, or migration, is what allows the separation of components. Now, the extent of this separation is determined by the partition coefficient of each component, which is a measure of its relative affinity for the stationary and mobile phases. This is where the art of HPTLC comes in, choosing the right combination of stationary and mobile phases to get the best possible separation. To visualize the separated components, we can use different methods like UV light or chemical staining depending on the nature of the components. And voila, we have a beautiful chromatogram, a snapshot of the mixture in its separated form. HPTLC is not just about separation though, it's also about quantification. By comparing the intensity of the spots or bands on the chromatogram with those of known amounts of the same substances, we can determine how much of each component is present in the mixture. With a solid understanding of the theory, we can now move on to the instruments that make HPTLC a reality. Now let's discuss the instruments and plates used in HPTLC. The high-performance thin-layer chromatography, or HPTLC system, is a marvel of engineering that consists of several key components. Firstly, we have the applicator. This is a precision instrument responsible for depositing the sample on the plate. It's like an artist's brush, meticulously laying down the starting point for our chromatographic journey. Next up is the development chamber. This component is the stage where the actual separation of compounds happens. It's filled with a specific solvent or a mixture of solvents that ascends through the plate due to capillary action, causing the components of the sample to travel at different speeds and thus separate. Then we have the detector. It's the watchful eye that observes and records the migration of the compounds. It's like a hawk, keenly observing its surroundings and capturing every detail. Now let's turn our attention to the plates. The backbone of any HPTLC system is the chromatographic plate. These plates come in a variety of types, each serving a unique purpose. The most common type is the silica gel plate, with its porous structure providing an excellent medium for compound separation. Then we have the reverse phase plates. These plates are coated with a hydrophobic layer, making them ideal for separating compounds that are less polar. And let's not forget about the bonded phase plates. These are specially designed plates with chemically modified surfaces, enabling the separation of certain compounds that might be tricky to separate on other types of plates. Each of these plates, with their unique characteristics, play a critical role in the process, enabling a wide range of samples to be analyzed using HPTLC. These instruments and plates are the backbone of HPTLC. Next, we'll look at how they're used in different development techniques. How are these tools used in the development process? Let's find out. High-performance thin-layer chromatography, or HPTLC, is an analytical technique that is highly versatile due to its various development techniques. The development process is where the separation of compounds occurs. The first technique we'll discuss is single development. This is the simplest form of development, where the plate is immersed in the solvent in a sealed chamber, allowing the solvent to ascend the plate by capillary action. Once the solvent front reaches a certain height, the plate is removed and the separated compounds can be visualized. Next, we have multiple development. This method is similar to single development, but the process is repeated multiple times. Each run increases the separation distance, allowing for better separation of closely related compounds. The solvent can be the same or different in each run depending on the desired outcome. Then we have gradient development, a more advanced technique. Here, the solvent strength is gradually increased during the process to achieve superior separation. It starts with a weaker solvent, and then progressively stronger solvents are used. This method is especially useful for separating complex mixtures with compounds of varying polarities. Now, let's touch on the development chambers. They play a crucial role in the development process. The two main types are the horizontal and vertical development chambers. The horizontal chambers allow for development in any direction, while the vertical chambers are primarily used for ascending development. Another exciting development mode is the automated multiple development, or AMD. This technique involves automated, repeated immersions of the plate in the solvent with drying periods in between. It offers excellent reproducibility and is ideal for complex mixtures. Lastly, there's horizontal thin-layer chromatography, or HTLC. It's a unique development mode where the solvent moves horizontally, offering an extra dimension of separation. Now that we've explored the development techniques, let's discuss how we scan and evaluate the results. Scanning and evaluation are crucial steps in the HPTLC process. Once the HPTLC plates have been developed, they're ready for scanning. This involves the use of a densitometer, a device that measures the intensity of light passing through a substance. In our case, it gauges the concentration of compounds on the HPTLC plate. The densitometer scans the plate line by line and captures data about the amount of light absorbed or transmitted. Now, let's move on to evaluation. The data from the densitometer is analyzed and interpreted. The aim is to identify and quantify the compounds present. Each compound presents a unique peak on the densitogram, which is a graphical representation of the data. The height and area of these peaks correspond to the concentration of the compound in the sample. We've covered the basics of HPTLC, but there's one more thing to discuss: the various applications of this technique. Finally, let's explore the wide range of applications of HPTLC. This remarkable technique has found its way into several diverse fields, each leveraging its unique capabilities to uncover the unseen. In the realm of pharmaceuticals, HPTLC is a trusted ally. It plays a critical role in the qualitative and quantitative analysis of drugs, identifying impurities, and ensuring the quality of medicines. By providing accurate and precise results, it helps maintain the safety and efficacy of our pharmaceuticals, ultimately protecting public health. Not just limited to pharmaceuticals, HPTLC also makes its mark in the food industry. It assists in food analysis, detecting any potential contaminants or adulterants that might be lurking unnoticed. From identifying pesticide residues in fruits and vegetables, to checking for the presence of harmful substances in processed foods, HPTLC ensures the food on our plates is safe to consume. In the world of forensics, HPTLC is a detective of sorts. It aids in the identification of various substances, from drugs and explosives to ink and dyes. It helps unravel the truth, providing crucial evidence that can bring justice to light. Furthermore, in environmental testing, HPTLC helps monitor the health of our planet. It can detect pollutants in soil, water, and air, providing valuable data for environmental conservation efforts. It helps us understand and mitigate the impact of human activities on the environment. Now let's touch upon some specific development modes of HPTLC. Automated multiple development is one such mode that allows for repeated development of the same plate, enhancing the resolution of complex mixtures. On the other hand, horizontal TLC, as the name suggests, involves the horizontal development of the plate, offering a different approach to sample separation. There are countless other development modes and applications of HPTLC, each serving a unique purpose and contributing to our understanding of the world around us. As you can see, HPTLC is a versatile and powerful technique used in a variety of fields. We've come a long way in our exploration of HPTLC. We've delved into the theory, surveyed the instrumental and plate varieties, explored development techniques, and uncovered its applications. Subscribe for more because you won't find me later. Until next time, keep exploring the fascinating world of chemistry.